Hello everybody, my name is Adel Lasmari. I am a PhD student from Monterrey University of Constantine 1, Department of Electrotechnique. I hope that you find the paper titled Optimal Energy Efficient Integration of Photovoltaic DG Irradial Distribution System for Various Load Model interesting and informative. Here is the outline of my presentation, which introduced by introduction, load model formulation, problem formulation, adaptive inertia white PSO, results and discussion, and finally conclusion. First, the integration of renewable energy in distribution network has become necessity due to the technical, economic, and environmental advantages, such as the reduction of total active power loss, improvement of voltage profile. In this paper, optimal integration of DG based on photovoltaic solar panel is presented to maximize the multi-objective function by using adaptive inertia white PSO. In this paper, a comparative study is conducted for various load models, which are constant, commercial, residential, and industrial loads. The multi-objective function based on maximizing the active power loss level, net saving level, short circuit level, voltage deviation level, environmental pollution reduction level. For the load model formulation, in this section we discuss about the mathematical time-varying voltage-dependent load model. The voltage-dependent load model can express as follows. Where Pi and Ki are reactive and reactive power at bus I, POI and KOI are the active and reactive operating point at bus I, and Vi is the voltage at bus I. MP and Nk are the active and reactive power exponents, which are assumed as shown in table 1. For the problem formulation, in the objective functions, the main objective function is used to maximize the APLL, NSL, SCL, VDL, and UPRL, which can be expressed by the equation as follows. Where alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 are the weighting factors. In this paper, alpha 1 is taken 0.3, while each of alpha 2, alpha 3, alpha 4 is taken as 0.2, and finally alpha 5 is taken as 0.1. The sum of the absolute value of this weighting is up to 1, as represented in this equation. Variables proposed in the MOF can be expressed as follows. In the distribution line constraint, we find the power conservation constraint. That means the active and reactive power injected to each bus should be equal to the total power of load connected to this bus, as follow in the equations. While for the bus voltage limits, the voltage monitored at each bus must be limited by maximum and minimum value, according to the following equation. For the voltage drop limit, the limit of the voltage drop can be formulated as follows. For the line capacity constraint, the power flow through any distribution feeder must comply with the thermal capacity of the line. For the DG constraint, we find the DG capacity, which should be within the allowable limits. The position of DG, then the number of DG, and finally the location of DG. In this section we discuss about the adaptive inertia-weight PSO. As we know, the basic PSO algorithm was first introduced in 1995 as a population-based stochastic optimization algorithm, which can be seen as a global search technique. The population of individual or swarm evolve through successive iteration. The inertia weight is one of the PSO's parameters, which was originally proposed to reflect the balance between the exploration and exploitation characteristic of PSO. The time-varying inertia weight of the proposed algorithm is represented in the following equations. Here is the equation of the velocity, then the position, and finally the time-varying adaptive inertia weight, where omega min and omega max are maximum and minimum value of the inertia weight. PS is the percentage of the particles which have had an improvement in their fitness in the last iteration. Here is the pseudocode of the proposed adaptive inertia weight PSO. In the section of results and discussion, first we talk about the test system. While the first test system is the standard IEEE 33 bus, which composed of 33 buses and 32 branches, as represented in the figure 1. The second test system is the standard IEEE 69 buses, which represents in figure 2. The convergence characteristic of adaptive inertia weight PSO algorithm are represented in figure 3. According to figure 3, it is clear that there is a difference between the load model studies in terms of reaching the optimal solution. For example, for the first test system, the constant and commercial loads are converged quickly with less than 10 iterations. The bus voltage profile of the two tested systems are represented in figure 4. For both test systems and for all types of loads, the voltage is within the permissible limits, which are plus or minus 5%. In addition, there is a similarity in the voltage profile in some buses, like in the buses from 3 to 13 for the first test system. This similarity is due to the optimal location and size of DG. The active power loss per branch for the two-study system is represented in the figure 5, which indicates the contribution of the integration of DG for the minimization of the P loss in each branch, which have different influences for each type of loads. This minimization is due to the size of DG for both test systems. The comparison among curves shows that the minimal P loss in almost branches is obtained for the industrial load. Also, the peak of the power losses per branch occur in the case of the residential and constant load. Table 2 represents the comparison of optimization results. A. The first test system. As shown in Table 2, there is a significance of influences of DG for all types of load. For example, for the constant load, the integration of DG in the bus number 7 with the size of 2.88 megawatt allowed to minimize the P loss from 210 to 114 kilowatt. Also, the minimum Vmin, which improved from 0.1938 to 0.9499. This note is for the second test system, which represented in table 2b. The conclusion. In this study, a multi-objective function based on the maximization of various indices, which are IPLL, NSL, SCL, VDL, and OPRL, was formulated to solve the problem of the integration of PVDG into a radial distribution system using adaptive inertia weights PSO to maximize various technical, economic, and environmental levels. The simulation results show that all the quantities are affected by the installation of PVDG, which satisfy all the constraints by the minimization of the losses of active power and the increase in the voltage profile. In addition, the maximization of APLL, NSL, and OPRL. In reality, loads are dynamic and are not always constant. So the study of constant loads is not effective in real distribution system. Simulation results obtained show that different load model can significantly and directly affect the planning of PVDG, which demonstrated the performance and effectiveness of the proposed algorithm. As a result, it is deduced that the use of realistic load model is highly important in PVDG planning studies. Thank you for your attention.